Good. Hi, everybody. Thank you for joining this webinar today. If you have any questions, there's a question tab on the left panel. Please submit those and we will answer them at the end of the presentation. I will now pass this on to Ryan.
Thanks, Abby. Good morning to all, and thanks for joining us this morning talking about high pressure atomization. We're going to go through some material relatively quickly, but I really want to cover on a few things of where application-wise HPA can be a great idea for you and your customer. So with that, without further ado, I'm going to get started here. So, starting off from a basic understanding of what a typical humidification system is, and I use the word typical as we talk about more of a historical aspect. One of the first things is boiling water using an energy source and then dispersing that through different means. So I assume most of you are familiar with steam generators, but as we go on and talk about different types of humidification, really breaks down into two categories. The first one being isothermal, which is that typical steam generator type system, and you're using an energy source to heat that water to then evaporate it into the air. Adiabatic, and where high pressure atomization falls, is using that energy that already remains in the air to evaporate that water itself. A perfect example of this would be kind of like that picture depicts. A little mister, I see those all the time when, kids are out on the soccer field or the parents, etc. Or another example would be if you're hanging a sheet out to dry that's wet and it naturally evaporates. So one of the benefits of adiabatic humidification is the free cooling aspect. It is a component that you can't get rid of. You get both cooling and humidification hand in hand. So some different types of humidification systems from a pictorial perspective. On the left, anywhere from a pressurized steam boiler to atmospheric steam generators, whether that's a gas source or electric source, or even another pressurized steam feeding the heat exchanger for atmospheric clean steam. On the right-hand side, the adiabatic typical technologies include pressurized water, which is that first photo on the left, and you'll see a lot more of that kind of pictures as we go throughout this presentation. Wetted media down below, and then ultrasonic depicted on the right side. Let's see. So typical adiabatic project categories. I don't know, it doesn't look like it's showing here. I'm having some difficulties on this slide. So what this is supposed to be, and sorry for this as I'm working through this Showtime platform here, looks like something is not going right. So I'm going to go to the next screen, but briefly talk about what we've seen as typical adiabatic project categories. So from an over 40% typically for DriSteem falls into the manufacturing sector. These are good applications that typically have a heat load and can benefit from that cooling effect. Next, from a market perspective, is data centers. At DriSteem, we would put this at about 33% based on our data, followed by university, lab, and office space. Where a majority of this comes from is, can they benefit from lower energy usage? And we'll definitely be talking energy throughout this morning and why HPA or high pressure atomization might be a good fit. The thing that you were able to see on the screen was the healthcare is new. So at least from the perspective of Ashrae. Ashrae 170 in 2017 added in high pressure atomization as an acceptable technology for healthcare facilities, given there are some guidelines around that. I'm not going to be going in depth on that today, but a lot of the things that we'll talk about from a component perspective are included in our standard system to handle that additional application. So looking at making a good application, really what I wanted to show in this slide and the following slide is it's not the typical geographic location that everyone's used to thinking, where can I get free cooling? Where is it hot and where is it dry? That would be very true if we were looking at 100% outside air situations. Obviously, we don't want to have to preheat the cold air if we're talking full outside air. But really what this is going to show is throughout the country, and then also throughout Canada as well, and other places globally, is there's applications that do make a good fit, whether it's a large load, whether it's got free cooling benefits, etc., is really application driven and not geography driven. So if we are looking at outside conditions and we are trying to employ adiabatic technologies, this chart is going to show where we're trying to target. So it's kind of buried in there in the psychrometric chart, but we're aiming for the letter C, which is right in the middle of the economization bubble alone. But outside of that, if we're trying to target that space, different technologies are employed to get there, whether that's economization, evaporative cooling depicted by EC, or mechanical cooling as we're trying to decrease the temperature and the humidity. So some examples of where, from a psychrometric chart perspective, of how many hours of operating time, if we're looking at outside conditions, apply and what technologies. So anywhere from Philadelphia to Denver, and then leaving the best for last, Las Vegas, in the sense of really the most, out of those three, the most applicable outside air conditions that can utilize evaporative cooling. So now that we know that, it's not necessarily geography based and it can be application based, in addition to outside air conditions, what is the atomizing system, and kind of going through what that system looks like. So the core principle of this entire system is using a pump to pressurize purified water, and I'll talk about water treatment in a little bit, and atomize this through orifices, also known as a nozzle. This can be done to several different zones or stages. But this system really consists of that pump, a VFD with a pressure sensor to maintain that outlet pressure regardless of the demand, and then staging valves to then allow you to have that controllability at the end user, whether that's in an air handler, in a duct, or in an open space. Along with that, you got pipings and controls, and the method to bring that water through the dispersion to the nozzles. The one thing that is required, at least from DriSteam's high pressure atomization, is water treatment upstream of that equipment. Now, whether that's DriSteam's reverse osmosis system, or if the facility has RO permeate already available, that can be used. But really what we're doing there with that water treatment is removing a majority of those dissolved solids to prevent white dust from occurring, essentially scaling and other minerals in there, which would obviously cause, I guess, dirt and a need for cleanup in those different applications. So what the water treatment would typically consist of, if you're bringing in city water, we would first dechlorinate it to prevent degradation on the membranes, followed by softening to increase that lifespan on the RO membrane from scale, and then reverse osmosis itself to generate that permeate, and then a storage method. So a basic operation of high pressure atomization is one pump station can feed many zones. It's not dependent. It's not a one-to-one relationship like we typically see on generators to dispersion from an isothermal perspective. But when a zone calls for humidification, that signal is sent to run that pump. And that pump will get up to speed through its VFD and maintain an outlet pressure. Once that zone closes, that pump internally recirculates and is ready for on-demand service for X amount of time. So what DriSteem has to offer in the marketplace, very comparable from a size perspective, anywhere from 250 pounds an hour to 5,500 pounds an hour. And really, we can combine multiple systems for larger capacities. We typically do this instead of using a larger pump for larger capacities, as it really gives us some redundancy for our end user as well. So I mentioned earlier, we do require reverse osmosis or better. From a nozzle perspective, we have 3 varieties, anywhere from 6 pounds an hour, 9 pounds an hour, or 13 pounds an hour, all which are based on a certain pressure. So if we're varying the outlet pressure, those capacities do change. One of the items from a marketplace perspective is a couple manufacturers use this style of pump. It's a water lubricated pump to have lower maintenance. 8,000 run hours is typically what the manufacturer recommends. And in comparison, what else is in the marketplace is oil lubricated, and that trade-off is, typically about 500 hours of time in between maintenance intervals for oil. So very low energy usage. As we talk about adiabatic technologies and we look at this energy comparison of what it takes to boil water compared to disperse it, let's say in high pressure atomization, is the largest size is using a 10 horsepower motor, which is a very low energy usage. So looking at duct and air handling operation, again, similar to isothermal, we will have an RH sensor in the duct or in the space that's going to generate that demand signal. We want to make sure that there is airflow during this period, so then we're, not just wasting that water and not providing any benefits to the end user. There are high limits for safeties, and that can be implored. So from DriSteam's perspective, we have 3 stages, and those stages are color-coded on the right there. The typical layout capacity is dependent on the physical size itself, but tend to end up around 15%, 30%, and 55% capacity per stage. With that being said, they can modulate all together. Obviously, giving you 100% capacity, you can mix and match, let's say the 15 and 30%, really looking at stages as how many inlet valves are there compared to how many combinations there are. With that, on the supply valve and the depressurization valve, there's a depressurization valve to turn off and to depressurize that system for when that signal says, I no longer need humidification. From an area type perspective, these are typically in manufacturing spaces. It'd be very hard to see this in an office space in that open space, right? This can be implored at different heights, but tend to need a minimum of 12 to 15 feet of height. Unlike, and we'll talk about this more as we go through the slides, but unlike air handling and duct applications where some of this water will go down to drain based on the efficiency, we need 100% efficiency in this space so we're not wetting equipment and not wetting floors, hence the minimum size. With this, I should mention, I kind of skipped over that bullet point, but with one pump station, we can control up to 16 zones. So if there are different areas inside of a facility that require different control parameters, that can be accomplished with one pump station, essentially one generator versus multiple, and controlled remotely at that specific place. We want to utilize the floor plan. So if we talk about that height distance, we don't want to be over critical equipment. These do require maintenance over time. Not a lot, but we want to be able to access that type of equipment. Regarding another type for area type, there is fan assisted. This is also in the marketplace and something that DriSteem has to offer. Really, this is going to promote better air movement and really decrease that absorption distance needed, because we're, instead of that gradient as we cool the air and as we humidify that air, this is going to get that turnover in that specific isolated space to get more dry and warmer air into it instead of the stick type manifold design. So some different capacities. These can be added essentially anywhere from 6 pounds an hour, which would be the FA2 style, all the way to 150 pounds an hour per fan for the FA4. Really, the benefit here is utilizing quick connect hosing and fittings, and helping on that install side of things as well. The one key note with FA3 and FA4 talking about air movement are this specific design that DriSteem has to offer. We're pulling air from the top and hitting that baffle on the bottom and then spreading the air out. So essentially bringing the hottest air in that building typically as heat rises, and then dispersing that. There's others on the market that pull up from the bottom. I guess the real risk to that is you can also pull condensate or that mist back up and cause dripping. So something that's a nice feature of DriSteam's fan assist. Let's see here. I do have a question, and I was going to do most at the end, but I'll answer this one as it relates. So how do you control multiple end user from supplying at different rates? So how that control scheme works, as we talked about, multiple zones to one pump station, is that pump's going to really maintain an outlet pressure. So if that, let's say the set point's 1,000 PSI, that pump is, regardless of demand, going to maintain that pressure, and it's going to ramp up and down accordingly. Now at the zone perspective, we're using one transmitter, let's say it's an RH transmitter, to control that valve in that area and control those nozzles. So if you have one in one, let's say area A, that could be running and area B is turned off because it doesn't need further demand. That's kind of how that control sequence occurs. So another picture again of a potential area type in a mechanical room where this is humidifying the space. Another depiction of up and over horseshoe design, in this case around the perimeter of the building. The one note here, we haven't talked about extensions. DriSteam's design includes extensions. So we can point those manifolds or that dispersion assembly upwards. And obviously we don't want to spray up into the building trusses and support network up there. And so we can direct and move around different obstructions with those flexible extensions. The other thing is, the reason why we point it up is so air has a means to escape. So if it's pointed up and the air is in that tubing, it has a way to go out that nozzle versus compressing during a shutdown cycle and essentially spitting water unatomized out of those nozzles. So sorry about this. I guess it doesn't like this format. Really, what I want to talk about on this slide is when we have a layout of a more, instead of like looking at this where it's very nondescript for a specific area, when you guys are working, guys and women working on different layouts, if we can get those layout plans so we can essentially lay over where we think a good route would be, so we can avoid different critical equipment, we can avoid, provide ourselves access, and all of our representatives are able to help with that and gather that information and work with us as the factory to find a good solution for you. So the main benefits, we touched on these to start with, but really the three main benefits that I really want to nail home on this is the cooling aspect that high pressure atomization can provide. If we can offset mechanical cooling, it's a very cost-effective way to do that and very energy conscientious. If we have large capacities of humidification, I have a very specific example of 2,500 pounds an hour, where that would take several traditional, gas to steam units or electric to steam humidification units, where one generator in that instance can provide that humidification need. And then zoning. Along the similar lines of large capacity, if we can have one pump station to feed multiple different zones or multiple air handlers, that can really be advantageous in the sense of project cost. So again, some typical applications include data centers, museums and storage, industrial and manufacturing, and universities. So cooling benefit, this is one of those things that we really want to be conscientious of, and we want to make sure these are being put into good applications where there is that excess heat in the air. So when we talk about these systems, anywhere from 10 to 20 degrees Fahrenheit of a temperature drop. Obviously, there's applications that fall outside of 10 to 20 degrees. I think I've seen up to 30 degrees Fahrenheit. Obviously, on an indirect situation where it's very hot and dry air. But as we look at this example and we talk about efficiencies, if we're looking at the same airflow and air volume and requirement for humidification, if we look at a supply inlet of 55 degrees Fahrenheit compared to 85 degrees Fahrenheit, and same like for like throughout, we're really looking at the evaporation efficiency. Warmer air can hold more moisture from a grain perspective, from pounds of water in the air. So the top scenario, looking at total capacity needed, our efficiency is not very good. It's 43% with a leaving condition of 41 Fahrenheit. And based on that inefficiency, that pump station needs to be larger, that water treatment needs to be larger throughout. So that budget cost could be anywhere from $90,000 to $100,000. And then if we look likewise, if we do have that energy in the air, whether that's a preheat source, whether that's heat source from the area, etc., we can take that same data and get 95% efficiency. Our total capacity needed is a lot lower. It's 526 pounds an hour, which drops the budget significantly. From a large capacity perspective, I know we talked about up to 5,500 pounds of humidification. It would take multiple units of isothermal generators to handle that same load. The one thing is these systems do use a lot of water, and that water is treated. So it's kind of economies of scale. So the smaller the system is, the more relative cost it is to handle that water treatment, pump station, etc. So really where we see the largest benefit, even though we have smaller systems, from an economic perspective, is roughly 1,000 pound per hour and above. Not to say that there isn't benefits to doing smaller systems, and there definitely are, but typically where we see the break point. So zoning benefit. If we have one pump station, we can feed 3 air handlers. If we were to do the likewise with isothermal generators, for example, to handle a certain load, you could potentially need, in this specific example, 3 generators per air handler. That can get quite costly. So make sure that when we talk about this, is 1 to up to 16 zones can be very beneficial for a pump station. So sorry again about the graphics as we work through this new platform. Really, there should be some lines in between connecting the 3 generators per air handler. So this example is one, a data center out of New Jersey that we supplied a high pressure atomization system, and they were comparing isothermal generators a few years back. And in the specific instance for the 10 air handlers that this facility had, would require 30 generators, which can be quite costly from a capital investment. Switching that over to high pressure atomization, they were able to utilize 2 pump stations to handle those 10 different air handlers, 1 dispersion, high pressure atomization dispersion per air handler. So what does that all mean? We've been talking really high level that obviously there's cost savings. And to give a little bit more concrete example, I wanted to run through an operating cost example with you. So the layout of this system is a manufacturing facility in Minneapolis. So first thing I always think of, since we're located in Minneapolis, the winters are very cold and can be dry. But I wouldn't naturally think there must be an opportunity to use that energy in the air. So this system is a mixed air system with a lower outside air percentage of 17.5%. From a room condition perspective, trying to maintain 70 Fahrenheit and 40% RH for winter conditions. And as we use it for free cooling on the shoulder season, so the spring and fall, driving that to 52%. The heat gain from the space, 620 mega BTUs per hour, and humidification load of 1,000 pounds an hour. So the rates I did use are listed on the screen, but I wanted to note the water rate is essentially the incoming and the sewer rate, as most places don't capture that we're sending this into the air and they're just doubling the sewer rate instead of putting a water meter, for example, to show that that's not the true drain rate. So really the meat and potatoes of the operating comparison, looking at these systems, is looking at first, what's your electric cost annually? The 2 notes for the electric resistive and gas to steam are these systems would be potable in this example, and why there might be a little bit of a apples to oranges situation, since high pressure atomization does require water treatment in the sense of RO all the time. Not to say that you can't use RO with these other technologies, but what we've typically seen is they tend not to use it if they can. So really the things that we're looking at, the top 2 lines are utility costs, but looking down to the 3rd line, talking about annual gas preheat cost. In this specific example, we do need to heat the air for these winter months. It's roughly $10,000 more, $11,000. But what we gain is the cooling savings from offsetting mechanical cooling. There is an additional pressure drop with the final evaporation media, which we'll talk about in components a little bit further. And then that water cost, not only the water we're putting in the air, but the water from evaporation efficiency and from our different components upstream, like an RO system and the pre-treatment. So with all said and done, the big hurrah, looking at operating cost of why someone might consider an adiabatic technology is that lower operating cost. The one piece I didn't have in here, as it is definitely variable based on different conditions, is that capital cost. High pressure atomization tends to be more expensive as you compare water treatment to non-water treatment. Let's see, I have a question here. I'll try to answer that one at the end. Let's see here. So atomizing system, this depiction it's very detailed drawing. This is something that is presented in our submittal documents as you work with us to understand what's required for these systems. These next few slides are going to be very quick and heavy hitter because obviously we can't see the detail on these. But essentially what my talking points are on these as we talk about different componentries and how they all sit together. So if we work from left to right, our left side is our pump station. We need water sent from the RO to it. We got drain lines, we got the pressurized storage tank, and then we have pre-treatment. So all these things on site need to be connected together. Some of you may be plumbing engineers, but I'm going to take the assumption that a majority are mechanical engineers on this presentation. So just something that we need to be cognizant of. There's things to connect. Same with wiring for power. So each control head on the pre-treatment requires a 120 volt circuit. The RO station and the high pressure pump station also require voltage, which can be variable. There's multiple different options on that. Control wiring, how do all these things communicate together? How do they communicate with your building management system? And how can we set you up successfully to understand that these things do need to be installed in the field? And when we're talking about, building management systems, what kind of protocols, how do you want to connect, what points we have to offer, and all those things can be found in submittal documents and manuals. Let's see here. So I guess I'll take that one at the end as well. Actually, I'll take that one right now. So indicating higher capital costs, what's the magnitude of cost difference between different technologies? So with that, from a capital cost perspective, as we talk about high pressure atomization, it might be 20 to 30% higher in that economic comparison than the multiple generators, whether that's gas to steam or electric resistive type units with multiple dispersion that do not have water treatment. So we're really looking at 10 up to 10%, and it really depends on situation from just the high pressure atomization if we're comparing apples to apples. So typical manifold, what this looks like and what this depicts here is it is stainless steel tubing that has saddle design where we're threading in nozzles, whether that's a plug, if we're trying to blind off a specific socket on that tube, all the way to number 2, which is an extension and a depiction of an extension with a nozzle on it for area type. Typical mounting, we see unistrut or channel dispersion with clamps. Another submittal type document, I showed this photo earlier talking about staging, but really from a software perspective, as we look at DriCalc, showing that dimension along with potential staging. So manifolds can, for air handling and duct, have up to 3 staging valves and also have 3 depressurization valves. So some typical submittal documents, so you get a flavor for what DriSteem has from a submittal perspective. Here's a drawing of an as-built for that specific aspect ratio. Final evaporation panels. This is a requirement to prevent wetting downstream of the high pressure atomization. And we'll talk a little bit about absorption distance in the subsequent slides. But this final evaporation media is to capture any liquid, non-vapor water from going downstream, whether that's cooling coil on the other side, a fan, a non-wet section of that air handler to prevent any liquid from going down further. Typical piping material. What the trick is, as we talk about small orifices and what DriSteem supplies and recommends for these systems, is we need to have hygiene at the top of our mind, so we're not taking oil and grease and plugging up nozzles. So what we typically use, it doesn't really matter the brand. We use Let-Lock double ferrule compression fittings for high pressure tubing, and instrument grade tubings for that cleanliness perspective. And really we want to think, how do we keep these nozzles operating and keep them operating as long as we can? So a little bit into the design, talking about evaporation efficiency. So if we look at chart inputs of 15 grains, which would be down at the bottom of this scale, and we want a leaving RH of 55%, We can target a 70% evaporation efficiency. These charts are something that we have published. Our sizing software called DriCalc does this automatically and looks at what is our efficiency so we can gain what our total load is. So if the space needs 280 pounds an hour in this example and we have a 70% efficiency, we need to supply that air with 400 pounds an hour efficiency, knowing that 120 pounds an hour is going to go down the drain, and that's our inefficiency in this specific example. So dwell time, one of the things is, and I heard this the other day, kind of the expectation was 6 to 8 feet, required for HPA. And really what, I commented on that is we typically see 2 to 4 feet. And what you guys and gals out there designing these systems for air handlers, it's really how do I maximize the efficiency, but minimize footprint and running up against those constraints of cost of air handler and that tunnel, essentially. So what we typically see is 2 to 4 feet downstream of the nozzles. The note for upstream is we're pointing those nozzles upstream, and we need a foot of distance in between our nozzle bank and the next closest thing upstream, whether that's a heating coil or anything else in that system. So as we get longer, as that tunnel length gets longer and that dwell time increases, the better our evaporation efficiency is. So these next two slides are going to be a specific example of 90 degrees Fahrenheit, and we're going to depict on this efficiency chart what the difference is between 2-foot absorption and 4-foot, with all things else the same. So looking at 90 degrees Fahrenheit coming in and 20 grains, and we go over to the right from a 2-foot perspective, we're about 75% efficient. Moving to the 4-foot example, looking at, again, 90 degrees Fahrenheit and 20 grains of moisture coming in, gaining that efficiency at 93% efficient. So again, I apologize for the technical difficulty here. What is on this slide is talking about the final evaporation media. There are cut sheets that we provide you, and the one that we use is a stainless steel design mesh, one of the lowest pressure drops in the industry from the perspective of face velocity, and roughly, if we're talking 500 feet a minute, it's about 0.07, 0.08 inches of water column pressure drop. So moving forward, talking a little bit about water treatment. This presentation is not going to go in depth on what's required or what design aspects there are from water treatment perspective. We have other resources of on-demand webinars for our HydroTrue water treatment line. But as we talk about the requirement for high pressure atomization, having reverse osmosis water or better, we do have that offering, and it does pair nicely from the perspective of capacity perspective. So I gave a little cutout of what our chart is, and the note I want there to present to you there, if you've not worked with ROs before, they are very temperature dependent from a capacity perspective. And really the industry standard from rating membranes is 77 degrees Fahrenheit. I think, as most of us know, that's not really the water temp that comes out of the ground. And we can use low energy membranes to give us that same capacity for relatively the same pressure, applied pressure and energy. So it does remove 98% of dissolved solids, the RO system, and what a complete system would entail, kind of depicted earlier, are dechlorinators, which will prevent the membranes from being oxidized from chlorine, which is in that water from a city perspective as a disinfectant, followed by water softeners in our case, Really what that's doing is preventing scale on that membrane. So if you think isothermal systems and you have untreated water, scaling and cleaning those systems is something that's required from a maintenance perspective. Same thing applies for RO systems. Even though we're not heating the water, the chemical side, we can help prevent scaling on that end. There are some options, as we talked about, bringing multiple plumbing connections to and from each system. We do offer skid mounting of these systems as a custom capability. Also with UV treatment is one of the things that is required for Ashrae 170 and is also a good technology to use for other applications as well. Some storage options really fall down to two categories, whether it's pressurized storage or atmospheric storage. The biggest note I always like making on pressurized storage is you have X amount of water pressure to transport that to wherever that end user may be. So if we know we have 30 to 50 PSI pressure set points, anything in between that that causes a pressure loss can attribute to not getting that water to the end user. So that's something we need to be cognizant of, is how do we transport that? So any vertical losses, any pipe losses from pipe velocity, any fittings, valves, etc. And the other thing as we talk about pressurized storage, the labeled capacities are its total capacity. We have to be cognizant of drawdown, and one side of that bladder is air, pressurized air on the initial setup side, and on the other side is the water side of that bladder. So that 80-gallon tank roughly will hold about 24 gallons of water. The atmospheric on the other side, we do need a means to pump that. It's got maybe a couple feet of positive pressure, and we obviously need a little bit more than that for most applications. So using a pump in this instance with that UV recirculation, and that tank physically would hold 165 or 300 gallons. So we do offer, and we do have some documentation around, if you're looking at a new project, what can we request of you as an engineer or a representative, if you're on the phone, to really make this project successful. So the normal things are your typical air handling and duct sizes. What are the air volumes? How do we, the stuff we really need to get to a load perspective. The other thing is we talk about reverse osmosis and that, what's on the water side? What challenges does that water provide us? And really, the bottom line to this whole thing is fill out what you can, and we can obviously work through the rest as we go through design. So I do want to talk about something common issues. We talked heavily about why high pressure atomization can be beneficial, typically from sizing large sizes or cooling potential, etc. But there are some hurdles that we should be aware of, and we should try to avoid as we can. So water supply quality, I think one case in my history was someone wanted to hook up non-RO water. And obviously the challenge there is the hygiene and keeping those nozzles operating. So we want to understand what do we need to do to make the system work properly and really give the customer what they're looking for. Low water pressure, I talked about this with the pressurized bladder tank. If we put the RO system 150 feet away, what's the motive drive getting it there? If we have to bring it up a couple of floors, we need to make sure that not only that perspective, but also incoming to our system. Each of the pre-treatment, whether it's a dechlorinator or water softener, there's a pressure drop that's associated with those. Low water temp. If we're designing systems and you guys are designing systems, what is the water temp? Will we have enough capacity from an RO perspective to make that work? Some control issues. What are the reset strategies in the spaces? What are the sequences? This HPA system if we're turning over and we want tight control on an RH, but we're turning over that air very frequently, that can cause some issues. So we need to be cognizant of what does that total system look like? How does ours interact with it? And things as simple as, if there's let's say a VAV box and there's zero demand that, on a carbon dioxide sensor, well, how are we humidifying that space? Things like that. Air handling and duct not designed for a wet section. This is actively spraying into that space. We need to be in a wet section. Area type nozzle placement. We need to be able to have access to that equipment, and we don't want it to be over a critical piece of equipment that could cause problems if it were to drip. I didn't touch on it, but our nozzle design is anti-drip nozzles, what they're called from the marketplace perspective, and they have a built-in check valve, roughly cracking pressure of 100 psi. So startup issues. When we handle these systems, and there's typically a startup and commissioning aspect that our agents, whether they're our rep or DriSteem factory personnel, when we get there, we want to start up with water and power. We want to make sure that there's building automation systems is set up and ready for us. Improper drain sizing. I'll skip over the salt for the softener because that's not really applicable for necessarily the engineering community, but improper drain sizing for water treatment and HPA. We need to be able to not have that back pressure so we don't cause undue stress to our systems. Piping systems not flushed, more of an install thing again. When we talk about long runs, additional depressurization, if we have a long run in our dispersion manifold, we're going to have to overcome that pressure. Otherwise, at the end of that line, we might not have 1,000 psi anymore. We might have 800. And we need to understand how that relationship works. And then isolation valves for servicing and troubleshooting. We've seen where we have to shut down the whole system where the isolation valves are built into the air handler. And from a lockout perspective, it would have been better to be on the outside. So I do want to wrap up on a positive note. So from a case study perspective, we talked about applications. And really the next 3 or 4, I can't remember how many I put in here, are kind of laying out what DriSteam's done, where our success stories are, and how can we replicate that. So it's missing the photo on the right, but essentially it's the picture of the case study. And what this specific one was for an aircraft paint booth. And from a quality perspective, they need to maintain relative humidity. And so in this specific instance, there were 16 separate booths for washing, blasting, and painting that aircraft component. And we used 5 high-pressure stations. So with all of these are on our website. Please feel free to go look at DriSteem.com. The other one, or the next one, excuse me, is a commercial printer. The printing space is very accustomed to using high-pressure atomization, whether that's the fan or manifold design. Excuse me. So really the telltale story here is we were able, by putting in this humidifier, to decrease their rejection rate or increase their profitability from their press output. It also lowered their electricity consumption, which was enough to qualify for a utility rebate. And each state and each county, there's applicable utility rebates as we look through those that can be applicable. And then we had another example of high capacity in that specific example. A data center. I briefly touched on this. The example, if you remember back to the 10 air handling devices or piece of equipment, this was one where it was able to reduce the cooling load by over 200 tons. And in this specific example, another offering that DriSteam has is, and something that engineering community should be cognizant of, is how can we take that unutilized evaporative inefficiency, and how can we reutilize that from a water conservation perspective. So in this specific instance, we did that as well. And lastly, as you know, from the great state of Minnesota here, can't forget the hockey arena. So what we did at this specific example, and feel free to read more up on this, is we improved their ice quality by essentially providing humidification to that space so that ice wasn't being that sacrificial humidity in that area. Also provide thermal comfort for those players, spectators and employees. This one was an area type example, and it was up in the catway due to the lack of space and air handlers. So really the takeaways from this presentation, I will open up for questions. It looks like I have 5 remaining that I have not addressed. So pros and cons. The pros, low energy usage. All adiabatic technologies, including high pressure atomization, are lower energy due to the fact that they use energy in the air to evaporate the water. HPA is capable of zoning. Again, 1 pump station for up to 16 zones. Accurate control. We're using on-off solenoid valves in those zones and in those stages from a zone perspective to really monitor and maintain that RH in that space. Minimal maintenance. Again, that pump that we use is a water lubricated pump requiring less maintenance than others on the market. Some cons, it does require RO water. So that does require more water usage. We're not, the RO isn't 100% in, 100% out as permeate. There's different recovery rates, typically around 75% recovery. So for every 4 gallons you put in, 1 gallon's going down the drain. Same with the evaporation efficiency. The cons, and as we notice throughout the industry that adiabatic technologies are growing at a faster rate than the typical isothermal systems, they still don't have the history that the traditional systems have. So with that, I am going to open up the questions page. So please, if you have any questions, submit them. Well, let's see here. What are the limitations of coil sizes and air handling and ductwork as it requires low velocity, keeping in mind that there are limitations of unit size as well as duct size in the building? So from our experience, I guess the largest one we've done is probably 12-foot dimensions. But really with high pressure atomization, it's kind of more configurable. So if you have a larger or a smaller application, we can handle that. As it relates to ductwork and velocities, as we know, a majority of the ductwork can be up to 1,000 feet per minute. That would not be something that would be a good application for HPA. If we're pushing that hard, that final evaporation media is really going to be limited to how well it removes, and essentially you're going to push liquid water through the backside of that. So something to be cognizant of. Typical supply water pressure. So on the front end, as we talk about water treatment, I guess let me first start off. The high pressure atomization pump station itself requires a minimum of 25 PSI. It does have a low water cutoff pressure to prevent dry running of that water lubricated pump. So minimum of 25 PSI, I think the maximum is 90 PSI in the pump station itself. Now, if the project does not have RO water and something that you're designing for a specific RO system for, let's say it's DriSteams, on the front end, we're typically looking at 60 to 90 PSI upstream of the dechlorinator. So as we talk about the pressure drops throughout, we're typically seeing about 10 to 15 PSI pressure drop at the dechlorinator, plus that at the softener. And then, so that right there is, 30 PSI. So, we're at 30 PSI for the RO. So similar for the RO station, if you already have dechlorinated and already have softened water upstream of a DriSteam RO, we're looking again for that 25 PSI minimum. So the next question was typical air pressure drop for the final evaporation media. So it is a linear curve, and I talked about 500 feet per minute. What that pressure drop was, I think it was 0.075 or 0.08 inches of water column. If we're up to, let's say, 700 feet per minute, we're probably shy of 0.14 inches of water column. Next question, is the AHU internal casing recommended to be stainless steel for the length of the absorption distance? The short answer is yes. It is a wet section. It is RO permeate. We do want to not have corrosion, and obviously needs to be watertight as well. We want to go completely drain and drain in the way of a drain port. Let's see, next question. So as you mentioned, velocity of 500 feet per minute would limit the duct size, as some duct with airflow velocity of 1500 feet per minute would require to enlarge duct when space is limited. What would be the solution? Appreciate your response. So if the airflow velocity is 1500 feet per minute, that would not be a good application for HPA in that specific area. So either A, enlarge the duct, or locate, if the facility has space in the air handler, or consider open space, open space type application with that is really the best answer. So even with that type of velocities, a lot of technologies would have trouble from an adiabatic perspective because of that longer absorption distance required. So even a media solution, like a wetted media solution, would not work well in 700 feet per minute, or ultrasonic, or compressed air over water, etc. If I guess the other comment on that, Andy, is isothermal could be another solution. I'm definitely not the expert to speak on that, but as we talk about absorption. During summer months, if usage is low, is there a risk of biofouling of storage since there's no chlorine? The answer is yes. So if the summer does not require humidification, or it's very low, there's a couple different ways of handling that. Hygiene is something I said we should keep top of mind. So the first thing is, if there is a load in the summer, we want to make sure that the system is left in auto. So we do have some hygienic features regarding flush cycles, both on the RO system and on the HPA system. So we can set, if it's no demand for, the standard is 72 hours, so 3 days. But if you wanted to essentially recirculate that water every 24 hours, that's something you could do. The second option is, if you have no load during the summer, or if it's maybe just 1 month out of the year, you can lay up these systems, draining the system and preventing and putting in a preservation cartridge into the RO is something that can be done. And obviously, when we start back up, there's a procedure to flushing and making sure that system is good. Next question is, can you address Ashrae 170 healthcare compliance as it relates to continuously circulating water to the humidifier valves and methods for water quality testing? So Ashrae 170 does require constant recirculation outside of the air handler. So think of it as one big out and back loop. And if it's not within that, if it's on the downstream side of the solenoid valve, so in your air handler, that would have to be completely drainable. But the water that's not in that air handler or inside that discharge side of the solenoid valve needs to be constantly moving. So from that perspective, DriSteam's solution to that is have that recirculation back to the atmospheric storage tank. With internal to that atmospheric storage tanks, it's constantly recirculating if there's no demand through that UV system. From a water quality testing perspective, Ashrae 170 doesn't give specific guidelines from like a CFU per milliliters. And really, as we combine those topics with Ashrae Standard 12 and Ashrae Standard 188, talking about healthcare water systems, really working with that facility to understand what their level of design they want to go to, from like an infection control specialist to the superintendent on site, the maintenance superintendent, and having testing ports. You need to be able to test that water and validate and verify that that water is safe and healthy. And then also, as we talk about final evaporation media, that liquid water or aerosols are not going downstream of that final evaporation media. Hopefully that answered from a high level perspective. Obviously, we can do more conversations around Ashrae 170 specifically. Is there any additional maintenance requirements beyond at the RO skid and pump circulator? So from a maintenance perspective, pre-filters to prevent physical solids going downstream need to be changed out periodically. We want to be making sure that chlorine and hardness aren't going to the RO. So checking that water, so back to the water quality perspective. And let's see, I talked about pump maintenance. Nozzles periodically need to be replaced. They are an orifice. They can get plugged. As I talked about, 2%, if it's a non-critical application, 2% of total dissolved solids are going downstream and occasionally need to be replaced. Same with, I guess the other thing is solenoid valves. With solenoid valves, they have so many cycles, and eventually the plunger in there and the coil will need replacing. Typically, that's even less frequent than biannually, unless there's some complicated application things going on there. How does high pressure atomization compare to ultrasonic benefits and application? So looking at ultrasonic, I view both of those technologies on the essentially the, two faces to the same coin. So ultrasonic is a lot lower capacities, still in the adiabatic family, but typically the largest size on the marketplace I think is 80 pounds an hour. So if we're daisy chaining a couple of those up for one application, that's something where high pressure atomization may become more advantageous when it gets larger from a load perspective. Both are the same side of the coin, as well as they're highly controllable from maintaining output set point. So I typically, I guess from an application perspective, break it on the size perspective. They both require RO water, regardless of manufacturer. So your water treatment requirement on the front end is the same. I know I'm a little over, so feel free, if you want to stay, I'll continue answering these questions. But if not, I appreciate your time today. So the next question is, are there applications where you would not recommend the HPA, whether not cost effective or not appropriate? So in situations that may not have a heat load, for example, if we're taking 100% outside air, it might not make a lot of sense to, let's say Canada, right? Let's say it's a office building, the heat load's low. We're not doing any recirc, it's 100% outside air. Would be an example where that preheat requirement doesn't necessarily offset the cooling benefits of that. Otherwise, critical applications that might be on the lower end of turn down perspective. So if we're talking like 10 pounds an hour, 15 pounds an hour, we're really on the small side of high pressure atomization, and we're really not going to be water efficient in comparison to other devices that can get that kind of controllability. So let's see, next question. I know you answered the capital cost, but I didn't catch what you were saying. You said 20 to 30% higher for something and 10% higher. So the 20 to 30% higher is as it relates to if we're comparing a generator example. And this is really, as we think back to the specific economic example, that was a higher load. If we get lower loads, talking about one of the benefits of high pressure atomization is a high load. But if we're talking that specific example, 20 to 30% higher would be comparing the isothermal generator without water treatment to, let's say, high pressure atomization with water treatment. The 10% comment is really taking that same example and looking at generator and dispersion from isothermal to just high pressure atomization, kind of ignoring that that might have RO with it as well. Let's see here. Chris, their post-presentation questionnaire you need to fill out for the PDF credit, the PDH credit, so that will be automatically sent out, I believe. If Abby, you can jump in, I think you know more about that certification piece.
Sure. No, there is no questionnaire that you need to fill out, but we will be sending a survey after the presentation is over. So please take that. Thank you.
All right, with that, I think I'm all caught up. If there's any other questions, I'll give it 30 seconds here. I know we're a little bit over, but I appreciate everyone's time today, and hopefully you're not all webinared out, and hopefully we provided some good information for you. All right, I think I'll cut it off there. Thanks again, everyone, and have a good afternoon.